a question to start with. Can anyone guess what famous computer science paper inspired the title for this talk? It's this paper here. What every computer scientist should know about floating point arithmetic. So a famous paper explaining floating point numbers. And one reason that's relevant is well, what every simulation expert should know about time. Well, the first thing that we should all know is not to use floating point numbers to represent time. And I'll go over the reasons for that throughout the talk. But yeah, this is one of the reasons that this is one of the things that inspired us to investigate time. We realized a lot of people were using floating point numbers, and some of the alternative representations weren't ideal. So we wanted to improve the way time was represented, and that led to a whole bunch of research on this topic. So we ended up publishing 3 papers, and we'll be going through each paper in this talk. So the first paper is called Taxonomy of Event Time Representations, and the idea here is that, if you go through the literature, you'll see a whole bunch of different words like that, that fit the template: blank time, like simulated time, or logical time, or real time. So what we found is that these words tended to be used inconsistently and interchangeably, and so we wanted to write a paper that really really identified what each word means and gave some formal rules to help distinguish them. So just I'd like everyone to think about now, do you know what all these terms mean? Like, for example, do you know the difference between simulated time and simulation time, or physical time and real time, or say virtual time and logical time? So this paper gives a clear meaning to all of these terms. So quickly here, I'll just explain some of them. Physical time is time, like it's time in the physical world. It's not a representation because it's the real thing. Simulated time. Actually, let me turn on a pointer so I can point these out a little better. So that's physical time. Simulated time here is it's a representation of physical time. So a simulated time, we tend to use years, days, hours, minutes, seconds, fractions of seconds, the same as we would when measuring physical time. Simulation time is, well, it's basically time that's used, any representation of time that's used for simulation. So it's really a category of representations. Simulation time includes simulated time, but it also includes virtual time and what we call discrete event time. What else? Real time is different from physical time, and it's different. It's not a representation of time. Real time means that there's a relationship between simulated time and wall clock time, which is when you actually execute the events on a computer. And what's the difference between virtual time and logical time? I'll explain that in a bit. So moving on, here's an example that shows a discrete event simulation where you've got 3 instances. The black dots are events associated with each instance. And you can see with these arrows that certain events can send messages to other events and other instances. And each event is assigned a time, but we're assigning time values using different representations. So we've got scalar time on the top. We've got vector time below each event. We've got virtual time down here, simulated time, and discrete event time, which is a combination of simulated time and those the counter on the bottom. So for any event, so for example, for this event here, we've got, for instance, on instance 2, we've got the scalar time of 5, vector time of 330, virtual time of 9, simulated time of T3. What we've done is we've identified a bunch of formal rules and relationships, which have come from the literature, but we've sort of put them all in one place. And I'll explain what this is in a second. But then the taxonomy is shown here, where we list the formal relationships between all the different types of time representations. So you can see there's a legend there. So the way you read this is you look for an arrow, and then you, depending on the arrow, you can read from the legend what it means. So for example, if we look at this arrow down at the bottom, in the middle of the bottom, we see scalar time and arrow going to causality. It's a solid arrow. So what that says is that scalar time is consistent with causality. Then we're going to go back to this slide, and we have to find what that means. So that we end up looking right here on the left. And so scalar time is consistent with causality. What that means that if you have two events A and B, and A potentially causes B, like the information can flow from A to B, then necessarily the A has a smaller time value than B. So if we back up again, we can see that in any case where two events, A and B, in any case where there's information can travel from A to B, the scalar time increases. So for example, from instance 3, if you're in the same instance, the scalar time increases. You've got 1, 2, 3, 6 on, for instance, 3. But also if you send a message from one event to another, like, here we're sending a message from this event at the top, which is a scalar time of 3, to this event here. So now the scalar time increases from 3 to 4. If we go back, what we can see here is that we see that virtual time is also consistent with causality, but simulated time is not consistent with causality. Simulated time does not contradict causality. And so that means that if A may cause B, then the time value of A is either less than or equal to the time value of B, but not necessarily less. So we see here, for example, that you have two events with two events where one event may affect the other, but the simulated time can stay the same. So the scalar time and the virtual time have to increase, but the scalar time can stay the same.
Rhys, can I ask you a very short question?
Yeah.
Does this imply that in the real world there cannot be simultaneity? That there is always, if there is a causal relationship, there is always possibly a very tiny, and we cannot represent it in the computer, but there is always a small delay, and that is the reason why you have a strictly smaller than relationship?
Well, yeah, so what this diagram shows is it shows under what time representations that's the case. So it says that, yeah, if you're using scalar time and virtual time, and you have one event that affects another, then yes, the time value has to increase by some amount. It might be a small amount. But if you're using simulated time, it doesn't have to.
And does that imply that in simulated time, we are making an abstraction of the virtual, like the arrow between virtual time and simulated time? Is that an abstraction relationship? Well, here, of course, in your case, it means is consistent with, but is there some aggregation, some abstraction happening there?
Well, Well, let me explain what that means. So yeah, and so I think probably the last one we'll cover, but yeah, virtual time is consistent with simulated time. And by the way, I want to mention that this is what actually distinguishes virtual time from logical time, because we often tend to interchange the two, but virtual time is consistent with simulated time. Scalar time is not necessarily, or logical time is not, any kind of not logical time is not necessarily consistent with simulated time. What this means, we look here, it says, okay, if we're looking at this formula there, virtual time is consistent with simulated time. That means if simulated time increases from one event to another, then virtual time must increase, but the converse is not necessarily true. So here we say that, okay, if the simulated, so let's look at a couple events here. If we're going from event at virtual time 5 to virtual times, sorry, let's say we're going to any event at simulated time t1 to an event at simulated time t2, then the virtual time must increase. So which you can see that very clearly. So any event in this t1 category has a smaller virtual time than any event in the t2 category. But if if the virtual time increases from one event to the next, the simulated time does not necessarily have to increase. So this event here is a virtual time of 2. This one is a virtual time of 4. Its simulated time is t1 in both cases. So in terms of abstractions, the key thing is that you could use different representations. So you can use there's different ways of representing virtual time or simulated time. You don't have to use these integers here, for example, for virtual time, but you have to follow these rules. So you're if you design a virtual time representation, it must be consistent with causality. It must be consistent with simulated time. If it's not, then you're not really using virtual time. You've created some other representation. So these relationships implicitly define, implicitly but formally define what each type of representation is.
Yeah, it's very nice. And by the way, the definition of abstraction is, of course, the formal definition is based on an implication relationship, and so you have it there indeed. And by your implication relationship between the two smaller thens, the T prime is consistent with T. That actually is the definition of an abstraction relationship.
Yeah.
Yes. So thank you for answering my question. I have another question, remark about logical time. And my many questions will make us run out of time, of course. But logical time, you typically find that terminology in the distributed simulation literature, and you have logical processes and logical time for each of these logical processes. Is that something which I don't see that here in your classification, the distinction between sequential and, well, there is sequential and parallel, but there is also distributed simulation. How should I see this distinction between distributed and local simulation in your figure? Is that linked to logical time or not at all?
Yeah, it's sort of indicated on the left here where you have wall clock time, because what the purpose of logical time, and we often get this confused in the simulation community, but logical time its only purpose is to capture causality, because that determines the order in which you can execute events. And that becomes really important in a parallel distributed setting, because you might end up executing events in all these different orders, but respecting causality, but not necessarily respecting simulated time. So, in a simulation context, you have a synchronous execution, asynchronous. So parallel DEVS uses a synchronous execution protocol, and there's also asynchronous protocols are also possible. So in a synchronous protocol, you very clearly respect virtual time. You basically do, if events have the same virtual time, you can execute them concurrently. Otherwise, you don't. Whereas asynchronous, you can go and sort of forget about virtual time in this, to a degree, executing events at different stages in a simulation, but respecting causal rules. So logical time, by capturing causality, it assists you in developing asynchronous execution protocols. Does that make sense?
Yeah, I'm not quite clear, but maybe I'll let you continue about the distinction between synchronous and asynchronous when you mentioned parallel devs is synchronous, because both sequential classic devs and parallel devs can be executed sequentially or distributed. But maybe we should discuss this at some other time.
Yeah, that's exactly.
There's the semantics of the language, which is independent of how it is executed, and then there is the parallel distributed execution, even sequential classic devs, which has no notion of parallelism, can be executed in parallel because the external transition functions, if you have a fan out larger than one, they can be executed in parallel.
Yeah,
you see what I mean?
That's exactly correct. I was oversimplifying a little bit by associating these devs with synchronous execution, although that was the intent. But yeah, no, it is absolutely true that they can both be done either way. But the diagram, okay, though, I think is correct, that if you do have a synchronous protocol, you're consistent with virtual time, and if you're asynchronous, you're consistent with causality. Yeah, okay,
thanks.
I should probably, I think I'm going to move on to the next paper, but we can come back at the end if there's time. So that's this paper on the taxonomy event time representations. The next paper is actually preceded the taxonomy paper. The next paper is called a quantum of continuous simulated time, and we gave it this paradoxical title because, I mean, if something is continuous, it doesn't have a quantum. So the paradox there was intentional. We thought, I kind of thought that was clever at the time, but in hindsight, I might have called this paper hierarchical analysis of time precision in discrete event simulation models, because that's more descriptive of what it actually is. So what we're going to do here is, first we're going to distinguish between resolution and precision. So time resolution pertains to these green arrows here. The time between events, so the times between when events actually occur. And time precision pertains to the time, these green arrows here at the bottom, the time between when events can possibly occur. So that the time between ticks, if you will. And so, when you have this time precision here, and you've got these events that are theoretically scheduled in between these ticks, what happens is these events have to be moved so that they align with these possible event times, and that introduces rounding error. So that's the difference between resolution and precision. To elaborate on that, we have these sort of parallel statements. So everything on the left is resolution, everything on the right is precision. So again, time resolution. So both of them characterize the frequency of time points, but time resolution is the frequency at which similar events occur, and time precision is the frequency at which event times are rounded. It goes on to say that, okay, for time resolution, you often have a time step that separates consecutive events. For discrete event simulation in a time precision context, you have a time quantum that evenly divides all event times. And then, having a longer time step, leads to larger discretization errors, and having a longer time quantum leads to larger rounding errors. So on the one side, you've got resolution, time steps, and discretization errors. On the other side, you've got precision, quanta, and rounding errors. So just to distinguish these two concepts. So focusing now on precision specifically, we can look at the difference between a fixed point representation and a floating point representation. So, a fixed point representation, you're going to have these rounding errors that stay fairly constant throughout the simulation, because the time between possible event times is fixed. For floating point representation, what happens is the precision will coarsen over the course of a simulation. So at the beginning of time zero, you've got these very small rounding errors because the possible event times are very close together. And as the simulation progresses, the possible event times get more and more spaced out, so your rounding errors increase. And by the way, that's what a floating point representation, that's what its purpose is. It's not that if you have a continuous quantity, you should use floating point. You use floating point when you want your rounding errors to increase in proportion to the magnitude of the value. So oftentimes that's exactly what you want. But in the case of time, I would suggest that's not what you want, because why would you want your simulation to get bigger and bigger errors as you progress? It doesn't make as much sense in that context. So that's one of the reasons why we say avoid floating point for time. So what do we do in this paper? Well, there's three. We focus mostly on these three types of models, but the theory works for any model. So there's a generator that outputs messages at fixed time steps. A reactive generator that does exactly the same thing. The outputs are at fixed time steps, but it can also take inputs at any time. And then there's a processor which can take inputs at any time and send outputs at any time, but always separated by this fixed response duration. And now what we do is we define this property called an optimal time quantum. For the generator, the optimal time quantum is a time step, which I think it's really intuitive, because that quantum will evenly divide all event times. For the reactive generator, the time step is again the optimal time quantum. And that might seem strange, because the optimal time quantum here, the time step, does not actually evenly divide all the possible input times, only the output. And for the processor, the optimal time quantum, again, it's the response duration. But even more strange now, because the inputs and outputs, you could have an input that occurs after pi seconds, for example, and the output would then occur after pi seconds plus the response duration. So all the events could be irrational numbers. All the event times could be irrational. Yet you still have this optimal time quantum that's response duration. So the paper describes why that's the case. So here's an example. Here you've got a generator with a time step of 24 seconds, and on the right here we're saying that there's this quantum of 24,000 milliseconds, 24 seconds for this whole composite model. And now we're going to add another generator to the overall model, and now the overall quantum for both of them combined is the greatest common divisor, the GCD, of these two generators. So the greatest common divisor of 24 seconds and 40 seconds is 8 seconds. And now as we add to that the processor 375 milliseconds, now the greatest common divisor is 125 milliseconds. So that becomes the optimal time quantum of the whole thing. And then we add, we keep adding more and more models, and the greatest common divisor keeps shrinking. When we can add more links going back and forth, and it doesn't actually change the time quantum. And finally, when we've added everything, we get down to this greatest common divisor of 5 milliseconds. So if we run this simulation just as you see it here, every event is guaranteed to be evenly divisible by 5 milliseconds. So that it makes sense that that's the optimal time quantum. But here's the key insight. This is the important part. What happens if we add an input to the composite model? And then there's a question mark there, because we don't know when the events are going to occur. So now the events could occur at any time. But we still say the optimal quantum is 5 milliseconds because for this whole composite model. Because we can imagine this whole composite model it could be embedded in a larger composite model. And then we would do the same thing as we've done here. We would take that 5 milliseconds and then take the GCD of that, and then with the optimal time quantum of other models in that larger composite model. And so as you keep doing this, eventually you get to the top of your system where you have a closed system. And so the optimal time quantum for the overall system is the one that applies to your simulation. But what the optimal time quantum does is it lets you reason about these precision levels in a hierarchical manner. So yeah, it's true that depending on the context, the events could happen at any time. But by assigning an optimal time quantum of 5, by acknowledging that, by identifying that property, you can reason about time precision hierarchically. Does that make any sense? This is it's a difficult concept to explain.
Yeah, it makes sense.
Yeah. So sorry.
Yeah, maybe a small question, which probably goes further back. You didn't talk about discrete time formalisms. You only talk about discrete event. Was there a particular reason for that? Because in discrete time formalisms, there is a fixed time step, which then typically, if you look at the scheduling algorithms for such for embedded systems, for example, they typically do this. No, they look for this greatest common divisor, and that is what is their internal clock then. Is there a particular reason why you did not include discrete time?
Only because it's sort of it's kind of a trivial special case. I mean, the generator was supposed to be like an example of a discrete time model.
Yes,
but yeah, it's true. Yeah, obviously, if you have all discrete time models, then it's obvious that the greatest common divisor will be the overall quantum.
Okay.
Yeah. So what we're saying here, okay, here we do cover it. Well, so I mean, traditionally, you look at models are classified as discrete time or discrete event, and then discrete event models are considered to use continuous time. But what we're saying here is you can take discrete event models and further classify them based on the optimal time quantum property, and you'll find that some discrete event models, like the ones we showed, have an optimal quantum that's positive. And so they don't, in a sense, they don't quite necessarily use continuous time. But some discrete event models have an optimal time quantum of 0, and so they're truly continuous. So we're sort of trying to challenge the traditional classification of models, introducing this extra sort of classification.
And is this because it seems to be that the ones that have discrete event that are not really, they don't really need real numbers, they basically have sort of a minimal time step. And so you could scale the entire system or the entire time base, and you could end up with integers ultimately.
Exactly,
And then the other one is where, for example, you have xenoness or whatever it may be. Maybe that's even too extreme, but where you keep dividing time by 2, by 2, by 2. And so obviously that will in the limit tend to 0. So there will never be this minimum quantum. Is that correct, or what example would you give of the optimal time quantum equals 0?
Okay,
what would be a good example?
I wouldn't use that Xeno example.
No, that's an aberration. No, because it's illegitimate, because time never progresses beyond the. You want an example where time does progress, but what would be a good example then of where the time quantum is 0?
Okay, I have a slide at the end of this section.
Okay. Yeah.
But so what we have here for discrete time, we've got the generator that we just showed as an example. And then in this category, we have the reactive generator and processor, which are discrete event, but they have an optimal, positive optimal time quantum. So just quickly, if we go to chapter 4 of Bernie's book, where DEVS is defined, there's a whole bunch of examples. And interestingly, so you might ask, okay, which of these models have a positive optimal time quantum? Interestingly, every single one of them does. So that just shows you the significance of this optimal time quantum property. It's not just a few models; it's every single model in this set of examples.
Yes.
This is one of the reasons why we say, another reason why we say don't use floating point for simulated time is because if you have an optimal time quantum, then you may have the opportunity to compute event times error-free, but you squander that opportunity when you use floating point. So that's, if in some cases you do want to have exact event times that are perfectly consistent with the specification, and having a fixed point representation allows you to do that. There's different applications of this. Well, one example is in model checking, where if you go through the literature, they often invent all these model checking techniques, but then they say, oh, okay, it only works if your time advance function or your elapsed duration is restricted to rational numbers. And so here's one example. Here's another example. Same thing. It says, okay, these time values have to be restricted to be rational numbers. But this is really selling the work short, because in general these DEVS models are not restricted to use rational numbers for these elapsed durations and planned durations. But when you introduce this theory from our paper about optimal time quanta, then you see that, oh yeah, okay, actually these model checking ideas could actually be applied to a much broader set of models. So yeah, they can be applied to discrete event models in which you have, they're discrete event, but they have an optimal time quantum. So that's one potential application. So yeah, to come back to this example, there are models that truly use continuous time. One example, these are two examples actually. One example is a quantized integrator, where you quantize the values in the y direction, if you will, the state values, and then you perform an integration. So when you do that, the event times are selected in a way that you don't necessarily have a quantum. And the other another example is a Poisson process. So basically, you're generating the event times randomly from an exponential distribution, very, very common technique. And obviously, because they're randomly generated, there's no quantum. So these ones.
Well, technically, they are not randomly generated. It is a pseudo-random number generator. So it does generate a finite number of numbers, and so you could argue that even there, in principle, you could map this onto integers.
Yeah, we actually do mention that, I think, in the paper. Theoretically, you could specify a model mathematically to use like a perfect random number generator, like a truly continuous random value. In that case, in that case, theoretically, the optimal time quantum is 0.
Yeah.
Then when you implement
by the way, the early simulators, like the GPSS simulators, they all used an integer time base, and so I think there are many examples of early simulators where integers were used and floating point was not used for exactly the reasons you've mentioned. But somehow we've drifted away from that. I don't know when and how.
Yeah, I guess, yeah. And so part of our the motivation behind this work is to encourage people to maybe get back to using using a fixed quantum, basically using integers, or what we might call fixed point time representations. And that's actually a good lead into the final paper of the three. The final one is multi-scale representation of simulated time, where we're trying to find a time representation that works in multi-scale contexts. So to sort of set the stage for this, here's a graph. Imagine, I was going to say, this is a graph of all simulation models ever created, plotted on this plot, where on the vertical axis you have the length scale, and on the horizontal axis you have the time scale. So in the middle you have models at about a human scale, 1 meter and 1 second. At the top right you have maybe computational astrophysics simulations of the universe, for example. And at the bottom left, you might have molecular dynamics simulations at a very small scale. Of course, this isn't actually a real plot. This is just an illustration. All the data here is invented just to show what it might look like if you could plot all simulation models ever created on a single plot. What you tend to see is that you would have a clustering effect where they cluster around sort of a human scale, or not too far, but of course you'd have some more extreme scales. And you'd also see an effect where the larger the length scale, the larger the time scale.
And why is this? Because if I think of vibrations in physics, they happen at all scales, and why are the ones that happen at a larger scale of a lower frequency, a lower length scale? Why are they? Do you know a reason why this would be? And is there, because this is invented? Do you have evidence for this? That there is this correlation?
It's fairly widely believed. Because if you want to do a molecular dynamic simulation where you track individual molecules, you're not going to make your domain the size of the universe. You're not going to have a model that in that case that you'd be at the top left. You're not going to have a model at the top left where you've got very tiny interactions, but you're simulating at the universe scale. On the other hand, you're not going to have a simulation that takes billions of years. I'm mixing things up here a little bit. So like you're not going to have a simulation that takes billions of years, but you're simulating individual atoms, and you're not going to have a simulation that's the size of the universe, but you're capturing interactions that take place at the femtosecond time scale. It wouldn't be tractable. So you will tend to have this correlation.
Okay, and I have to think a bit more about this, whether this is due to inertia or just pragmatism of humans. I have to think a bit more about this. Yes, but if you have more documentation about this, I'd be very interested.
I mean,
like empirical evidence of this being the case.
I mean, okay, this is a very if you look at the literature review in this paper, you'll find a bunch of general references on multi-scale modeling, and they have plots. They tend to be a little bit more. They tend to have they're a little different. I mean, they tend to be a little simpler, but basically the trend is widely.
And okay, I see where you're coming from, because in the multi-scale modeling community, we basically say we will divide this in strata, and we will move between these different scales instead of having a single model which covers everything. But there may be a certain literature bias there, because it is the community that says we want to divide this into layers, multiple layers of detail, and we want to move between them. And so I don't know. If that is the literature, then I can understand where they're coming from. Okay. I'll look at the references.
I'm going to have to go through this fairly quickly, but one thing we cover in this paper is what scale means, and we just say that scale is not just simply what distances or durations appear in your model. What scale really is it's the degree, look at the underlying text, the degree to which distances or durations must be altered to have an appreciable effect on something you're interested in measuring. I just give an example here where you've got a particle bouncing around in a big compartment, and let's just say that particle is much smaller than pictured there. So it looks like you've got two scales because you've got a really small particle and you've got a big compartment. But actually, we would, if you simulate this, what this could actually determine is the length of time between bounces, and that depends only on the larger scale. It only depends on the scale of the compartment. The scale of the particle is not actually, it doesn't affect the results. So in this case, we would say this is a single scale model, even though it has a small distance and a big distance. But now if we add multiple particles, and now we could predict not just the bounces, the time between bounces off the compartment, but we could predict the time between collisions between particles. And that depends on both the radius of the particles and the radius of the compartment. So on the right, we could argue that this is a multi-scale model. So that's just trying to clarify the meaning of scale.
I see.
And this brings us to what the issue is that we're trying to solve in the paper. And the issue is this: is when you combine large and small scale models, you're going to get rounding errors when you round up your time values. And the rounding errors are going to be determined by the longest time scales. But the effect of those rounding errors is going to be determined by the smaller time scales. So if the two scales differ greatly, you're going to get significant distortions in the small scale behavioral patterns. So that's the issue there. So if we look at different standard representations, fixed point versus floating point, what we see with fixed point time values here, and just to explain this a little better, what we're doing here is we're taking a model that has a short time scale and a long time scale. So a multi-scale model with two different scales, and they're integrated together. And then when we run a simulation, we run a whole bunch of simulations, we get these results, and they should be, the result that we should get should be around 76 or 77. So all these results here are good. So just to show you that the degree to which this is multi-scale increases as you go up to the right. So that the short time scale gets shorter and shorter as you go up, the long time scale gets longer and longer as you go to the right. So it becomes more multi-scale, more discrepant as you go up into the right. So what we find here is that everything is fine because your errors are all consistent until you get to a large discrepancy, at which point you just run out of, you overflow, you run out of bits in your time values, and so the simulation just fails. And now you might say, okay, well, does floating point solve that problem? Because floating point, you can represent huge discrepancies in your numbers. So you represent really huge fractions or really small fractions. Well, what happens if you use a floating point numbers? You get something like this, where okay, your simulation doesn't necessarily fail, although here it does fail in a few cases, but doesn't necessarily just completely crash as you get to larger discrepancies in scale. But what happens is it degrades. Your results get all messed up. And so if at very large discrepancies, it becomes quite obvious that something is going wrong. But there's a sort of danger zone right when your results start to degrade, where you might not notice that you're going to get bad results, but you might not notice that's happening. So this is another reason why we recommend it against floating point time values, specifically for in a multi-scale context, because you run into this danger where you get these large errors. Again, it's the errors from the larger scales affecting the smaller scales. So I've almost out of time. So what we've done here is we proposed a multi-scale time representation that that it provides the benefits of both fixed point and floating point. It provides extensive range and fine resolution where needed, so it does what floating point is supposed to do. You don't need to agree on a common precision level, so everyone can use a different precision level, and there's various data types. It uses 64-bit values where possible, so it's fairly efficient, and it uses arbitrary precision time points where necessary. So just here's an example of what you would do using this method. You could have a composite model where each model here has a specific precision level that's specified by the modeler. One modeler could use milliseconds, another one could use femtoseconds. Some models have no time scale. Whatever they choose, you can integrate these together. We had to come up with some new theory in order to make this possible. One of the theories is this idea of multiscale perceived time, where if you have different models at with different time precisions, they perceive the current time differently. So to simplify things, we came up with these time precision levels that we call forest, tree, branch, leaf, which are different by a factor of 5 in our actual representation. The time scales differ by an order of 1,000, but we couldn't actually plot that all in one plot. So just to simplify the illustration, we've used a factor of 5. But you can see a model at the forest precision level thinks the current time is 375, whereas one at a tree level thinks it's 425, and perhaps the actual time value is 448. So there's this idea of models perceiving the time differently. And then that introduces a special form of time advancement, which we call multiscale time advancement, which in these 3 cases here, you're advancing time by the same amount, like 100 leaf units in this example is equivalent to 20 branch units, which is equivalent to 4 tree units. But in each, depending on what model is advancing time, what model is scheduling a new event in the future, you end up with different future times. So with this theory, we've come up with a set of data types and data structures that implement it. And just to illustrate, there's a bunch of fancy bookkeeping you need to do to make this work. You end up with this time queue, where when you schedule events at certain planned durations in the future, you end up recording these planned phases, which are measured from the beginning of an epoch. And all events are always scheduled within either the current epoch or the next epoch. But there's actually, there could be any number of epochs. So this is how you can run really really long simulations, but you're only scheduling within 2 epochs at any given point in time. One inconvenient aspect is you end up with the possibility of infinite elapsed durations, because under certain conditions you might have a model that goes passive, then a very long time elapses, a whole epoch, and then it receives a message. And then if that's the case, this will rarely happen, but if it is the case, you'll have an elapsed duration that can't be represented, and so it ends up just giving you elapsed duration of infinity. So the one inconvenience of this representation is that you do have to, if you want a robust model, you do have to have like an if statement that says, okay, if the elapsed duration is infinity, then handle that case separately. Other than that, all of this complexity is basically hidden from the modeler, so they get the benefits of multiscale time without having to actually worry about the details. So yeah, just to summarize, a fixed point representation could be considered a naive approach. 32 bits is too coarse, but a 64-bit fixed point time is good for single scale applications. Floating point time is error prone, and we don't recommend it. 32-bit is almost unthinkable. 64-bit floating time is quite common, but again, it runs into these issues that we've talked about. Rational numbers is possibly overkill, but it is an interesting option. Arbitrary precision could be considered a brute force approach. Multiscale is the most difficult to implement, but it is the most scalable of these options for representing time. Okay, so that's this paper, multiscale representation of simulated time. The previous one was the quantum continuous simulated time, and then there was the taxonomy event time representations. All right, that's it.
Very nice, very nice. I should start including this in my lectures, in my modeling and simulation lectures. Maybe next year I will include it. Maybe one more question before I have to go. I've often wondered in any real world system, there is time translation invariance, and Bernie also says this in theory of modeling and simulation. And also, if you look at DEVS models, they only have a notion of time advance, and they have a notion of elapsed time since the last event occurred. So everything is relative. And this, of course, makes sense, because there is nothing in the world that is really dependent on an absolute zero. And nothing depends on when the Big Bang occurred, and the dynamics would change depending on how long ago that was. Maybe I shouldn't say that, and that's maybe a philosophical discussion. But typically, the laws of physics, whatever model we have of dynamics, is time translation invariant. And the only reason why we come up with this absolute time is because we somehow want to plot this along some axis. And so I've often wondered if there isn't something deeper there, and maybe we should not be so focused on this absolute time. And of course, you see in the the abstract simulator of Bernie, he has this Tn, the next time, and that's an absolute time again. Although internally everything is relative. So I don't know what your idea about this is, that somehow there's something strange that we then again make it absolute, which isn't really absolute, because it's always from an arbitrary starting point of our simulation.
Yeah, I think a lot of it's just convenience, because if you you could have all time values be relative to the current time, for example, and you could get rid of this absolute notion of time. But the problem then is it becomes inconvenient, because you have to keep adjusting. All these durations keep changing. Like if you have all these events scheduled in the future, and then the current time advances, well, now you have to sort of subtract off from all the different events that you've scheduled. Just practically speaking, you need some kind of reference point, just so that you don't have to keep on changing all your time values. So usually that reference point is just time equals 0 at the beginning of the simulation. In our case, we kind of use the beginning of these epochs, and that allows us to do longer simulations. But I think, I think it was a good insight of Bernie's, a very valuable insight, to have these time values be represented wherever possible relative to the current time with the elapsed durations and the planned durations. That actually allowed us to do a multi-scale representation where at the modeling level, you're using these 64-bit durations, because the time is always close to the current time. But at the simulator level, we use these arbitrary precision, we use epoch time values, and we have this absolute.
Because if you see that when we determine the imminent set, all we look at is the remaining times. So it's a collection of remaining times for each of these atomic models. And they are all smaller than or equal. Well, some of them might be infinity, but they're all smaller than or equal the time advance, because you keep nibbling off. So they're all relatively small numbers.
Yeah. But I think if you have lots of stored events, you want to implement it with some kind of reference point. Theoretically, it doesn't matter, but I think practically speaking, you want to choose some kind of epoch. Again, it's really a convenience for implementation. But I think you're right on a fundamental level that we don't really care about the absolute time point.
anyhow, thank you so much. Brilliant presentation and also brilliant work. No, thank you so much. I'm afraid I have to go, and I'm sorry for the many interrupts. Others probably also have questions. So, but I will have to leave now.
Yeah. Okay. Yeah. Thanks a lot, Hans.